Thanks so much to Uncorked again for hosting us. Yay! They give us a wonderful venue for doing this, and that's why it's very nice to see so many people who have patronized them already. I urge you, if during the talk you realize I need another beer or glass of wine, please go on up. They'll be happy to serve you. Right now, just want to remind you, please turn off your cell phones. And I am going to be putting around, right after our speaker finishes, comment forms that you can tell us how you like the event, maybe what other topics you'd like to hear about. That's what we're really interested to know. What else do you want to know about the laboratory, or any way that we can serve you better with these events? So the next Science on Tap is Thursday, April 20th. Science on Tap is always the third Thursday of the month, and it's always here, so you can mark your calendar. We don't yet have that speaker lined up, but be assured it will be another scintillating speaker on a science subject. That's why I want you to fill out those comment forms. Give us ideas of what you'd like to hear about. Many of you said you wanted to learn more about LANSCE, hence Gus, our speaker tonight. So here's how Science on Tap works, for those of you who haven't been here, or any of the On Tap series. We begin with a short presentation, 10-15 minutes, by our expert, who will apprise you of some cool stuff that he wants you to know about, putting out there the different topics that might cause you to have questions or want to start a conversation about something. And that's what we want. We'd like you participating in a conversation about science tonight, or engineering or technology. Science is a general term here. Please, go ahead and peel off of the kinds of subjects that our speaker brings up, and we really do expect you to participate. It's not just ask a question, he gets to answer. You might ask a question, and a guy over there might have something to pipe up and add into, and then somebody over here, and that would be grand. That's what it's all about. So please participate. It'd be very nice. So let me introduce tonight's speaker. Gus Sinnis is Deputy Associate Director of Experimental Physical Sciences and the LANSCE Facility Director. He's been interested in physics, he says, his entire life. His dad was a physicist at Princeton Plasma Physics Lab, and he used to go to work with his dad sometime and see the big machines that his dad played with there. In college and then afterward, Gus delved into particle physics when he worked at CERN in Switzerland, and do they call it DESY?
Daisy.
DESY in Germany. Then astrophysics questions and observations piqued his interest. So he changed to astrophysics, working at institutions from the University of Wisconsin to the University of Hawaii. He's been all over the place. And now he's here, enjoying the great outdoor sports that we have on the Pajarito Plateau. It sounds like our wonderful outside environment attracted him here, as well as the biggest machine that the laboratory has, which is the LANSCE LINAC. So let's hear about the latest going on at LANSCE from Gus. Please welcome
Great.
Gus.
Thank you. So thank you for coming. It's my pleasure to be here and tell you a little bit about what we do down at LANSCE. So I handed out little sheets to kind of give people an orientation. And on the front of the sheet is a picture of the LINAC itself. So the LANSCE LINAC stands for Linear Accelerator. It's a proton accelerator. It was built, had first beam in 1972. So it's quite an old machine. When it was built, it accelerate protons from at rest to 800 million electron volts. And we accelerated a beam that had a power of a megawatt. Okay, so that's 1 million watts of power in a proton beam that's about this wide, right? So if you get yourself in that beam, it'll burn a hole right through you. It can burn a hole through the steel of the beam pipes. So an incredibly powerful proton beam. So powerful, in fact, that even now, so 45 years after it was first commissioned, a megawatt is kind of the highest power machine that there is in this country out at Oak Ridge, right? So they accelerate protons to a GeV, which is 1,000 million electron volts, and have a similar power of a megawatt that we have here in a machine that we built 45 years ago. So it's a pretty amazing machine, and even 45 years after it was built, we're still doing some really amazing things with it. So what you see on here is not only the LINAC itself, the linear accelerator, but we have 5 what we call target stations. So the protons get split off and go to these 5 different areas, and they do different things in those different areas. And so there's a huge range of research that we carry on at LANSCE. And those 5 target stations, some of them have multiple flight paths. So in total, we have 16 flight paths down at LANSCE. So we can have 16 or more experiments going on at the same time. And the machine, when it runs 24 hours a day, 7 days a week. And we typically run for 3 weeks, then we take a week off, and then we run for another 3 weeks, and we repeat that, and we do that for about a 6-month period, and then we take off time of about 4 months, 5 months, and do some extended maintenance on the machine. Because keeping a 45-year-old machine like this running in a nice, perfect state, which it has to be to keep control of that beam, is actually a really difficult job. There's about 120 people working on the accelerator at any one time. So it's a massive effort to do that. And it takes about 20 megawatts of power from the city to get that 1 megawatt of proton beam. And so it's the biggest user of power in the county. The supercomputer center up at Los Alamos is coming up on us now. They're using almost as much. And when they put in the newest computers, they'll actually be using more than we are. So it's kind of amazing how much power computing takes as well. So one of the first places that you see on here is called the Isotope Production Facility. So what this is a facility that's run by the Department of Energy, Office of Nuclear Physics. And their main job is to produce medical isotopes that are used in treatments and for medical, not just medical research, but medical treatment of people. And so cardiac imaging is one of the big things they do. So they produce an isotope known as strontium-82, and it's injected into your heart, and then they have scanners that look at the radiation that comes from that, and it can see if you have any clogs in your heart, any places where the blood stops flowing. And we produce enough isotope to treat about 30,000 people a month with that. So us and Brookhaven National Lab produce all of the strontium-82 for the country, and we're about 60% of that production. The other thing they do is they do research for new methods of medical treatment, how to use developing new radioisotopes. And one of those that's very exciting is called actinium-225, right? So it's a very heavy isotope, and it decays by an alpha particle. Actually, it decays via emission of 4 alpha particles. So alpha particles are very heavy. And so when you normally go for cancer treatment that uses radiation, they'll use X-rays, right? And the problem with X-rays is they can travel through a lot of material. And so there's kind of a race where can we kill the cancer before we kill the patient, right? Because we're killing a lot of healthy tissue. The nice thing about an alpha emitter and an alpha particle is that because it's heavy, it gives up all of its energy in a very short distance. And so if you inject it in a person and it travels to the cancer site, and then it just decays right there, and all the energy is deposited in the tumor and not in the healthy tissue. And so the FDA is actually now undergoing clinical trials, but to do those clinical trials, they need to produce this actinium-225. It's actually pretty difficult to produce. You need at least 200 MeV of proton energy to produce a substantial amount of actinium-225. So there's a nationwide effort that includes 3 laboratories, us, Oak Ridge, and Brookhaven, to try to produce this actinium-225. On the back, there's this graphic down here in the bottom right as you're looking at it. And what this is a patient that had cancer, and it had metastasized throughout their whole body. So PSA level when he started was 2,900 nanograms per milliliter. They underwent 3 treatments of this targeted alpha therapy with actinium-225. And what you see is, the disappearance of all of the lesions very quick after the first and the second and the third treatment, and then the PSA level going essentially to non-detectable. So this is looking like a really promising cancer treatment, and we're one of the few places that would be able to produce this. And so this is I think one of the really exciting things that we're doing. NBC came about a year ago, did a special on this, that if you Google it, I think you should be able to find it. So that's a kind of a cool thing that we do. The other cool thing that we do, so if you go down further on here, there's a place called ultra-cold neutrons. Okay, so here what we do is we use the protons to create neutrons. So they hit a tungsten target, and the spallation, so what you do when you do the spallation is when you break up nuclei. Okay, so the high energy proton comes in, break up the nuclei in the tungsten, and neutrons come off. Those neutrons have a high energy, so what we do is we cool them down. Very, very cold. So in the ultra-cold neutron facility, those neutrons have an energy of a billionth of an electron volt. Okay, a nano electron volt. So if a neutron of that energy was coming up, started at the floor, it would get about a meter above the floor, and then the gravitational potential would turn it around. Okay, and so you can actually trap a neutron of such low energy with gravity. The other way you can trap them, they also reflect off of walls, okay, because they have a wavelength similar to the wavelength of light. So things that reflect light actually will reflect ultra-cold neutrons, even though higher energy neutrons will penetrate a lot of material. The trick, what people in the experiment here, so what you'll see on the back, on the left at the bottom, is kind of this bathtub. That's actually known as a magnetogravitational trap. And so the person sitting in there is setting the scale for this, but those little cubes at the bottom are actually very powerful magnets. And they're arranged in a very complex configuration so that the magnetic field is very strong, very close to the surface, but it drops away very quickly. So when a neutron with a certain spin comes and gets close to that wall, it'll actually be reflected by the magnetic field, and it'll never actually touch the wall. And so this is called a magnetogravitational trap because the magnetism traps the neutrons from hitting the wall, and then we use gravity to keep the neutrons at the top of the bathtub, right? So they don't get past the top of the bathtub. And so the things we use this for are for studying fundamental properties of neutrons, which gives us insight into fundamental laws of nature. And so one of the big things we do is measure the lifetime of the neutron is actually not very well known. And so you generate these ultra-cold neutrons, you dump them in this bathtub, and then you watch how they decay with time, and you can measure their lifetime. But in order to do that, you have to make sure that the trap doesn't lose neutrons through other ways, right? And so that's the whole secret of this magnetogravitational trap, because if neutrons hit a wall, they can disappear, and then you'll think a neutron decayed and get the wrong value for the lifetime.
I thought neutrons were unaffected by magnetic fields.
So their spin, they have a magnetic moment from the spin, and it's that spin interaction with the magnetic field that you can actually reflect them. But you'll only reflect a certain polarization. So you'll reflect half of them, and you'll get rid of the other half. And so you have to spin polarized neutrons before you put them in this trap, so that you're only measuring the ones that you know reflect, right? Because you don't want the ones that won't get reflected in that trap, because that will ruin your measurement.
Can you reverse the fields and look at the other component?
So these are fixed magnets, so you can't do that, right? So these are very strong fixed
So
magnets.
you've only determined it for one polarization.
That's right, but the assumption is that the neutron lifetime is independent of the polarization of the neutron. That would be a really exciting physics result if the lifetime actually depended on the polarization.
Build another one with them.
Yeah.
That's the other way.
So we do a lot of work. So there's a proton radiography facility. I can talk about that if people have questions about it. One of the other things that I did want to talk about was some of the work that we do at the Lujan Center. So the Lujan Center is really built to do studies of material properties. And so there we have a very complicated neutron spallation target. We used to run 16 flight paths just in that building, doing 16 different experiments at the same time. In the last few years, we've kind of coalesced the facility, and now we run 7 flight paths, 3 of them for material science and 4 of them for nuclear physics experiments. But one of the nice things about a neutron source that's generated with protons is that the protons come in pulses. And so they have a very well-defined arrival time on the target that creates the neutrons. And so we know the time that the neutrons are generated. And then we measure in the detectors in this facility the time that the neutrons arrive at the experiment. And so because we know the distance from the target to the experiment, we know the time, we can then calculate the velocity of the neutron. And from the velocity, 1/2 mv squared, we now know the neutron energy, right? So we now have energy resolved measurements of these neutrons. And one of the cool things about that is that if you look at different elements and different isotopes, you'll see, and you pass neutrons through them, they have spectra, neutron absorption spectra, just like atoms have absorption spectra for light, right? And so the different energies that neutrons are absorbed from an element or an isotope actually form a unique fingerprint of that isotope or element. And so by selecting certain energies of neutrons, you can actually look only at certain isotopes and elements in an object that you're looking at in the neutron beam. And so we do neutron radiography, and we do it on static objects, and we can rotate the object around, so actually do 3D tomography on objects, and do element by element tomography. And so the other picture on the back is actually from a nuclear fuel rod. So this was a uranium oxide, and then what's shown is we've selected out only tungsten in the fuel rod, and so you can see how tungsten has diffused through the material. And so the nuclear energy community is very interested in this technology, and this is one of the only places in the world where we can do this. So this is another one of the things that, you know, we just do an enormous range of physics here and really do things that aren't done anywhere else. And so for me, it's a very exciting place to work. I've been in the position I am for about a year now, and to me, it's the greatest job there is. So with that, I'd like to, open up the floor, take questions. Are there other parts of the facility you'd like to hear about? I'd be happy to talk more about that, but I didn't want to just sit up here and ramble for on and on, because I could go on as long as you want me to. Yes, Linda?
So Gus, is the Lujan Center physically connected in some way to the LINAC?
Yes.
Yeah.
So it's underground, so you don't see it. So there's actually a switchyard. There's a big building there, right? You see that big building,
Right.
and just before that building there's a mound, and the beam line, there's a switchyard there that's got a complicated array of kicker magnets that kick some of the protons over to the Lujan Center. So they go under the road in a beam line, and then there's actually what we call the proton storage ring. And the protons then get compressed. Because we want to do the neutron time of flight, we want the protons to be in a very small bunch. And so when they come out of the accelerator, they go on for about 1.6 microseconds, and is the bunch length. They go into this proton storage ring, they can compress down to about 200 nanoseconds, 200 billionths of a second. And that's the bunch that hits the spallation target. And with that 200 nanoseconds, we can now get very good resolution on the neutron energies that come out.
Could you say a little bit about the proposed experiments for Marie?
So the Marie facility is a $4 billion facility, right? And so Marie is a little bit different than LANSCE. It'll actually, the beam line will go on the north side of the current LINAC. It'll be an electron beam instead of a proton beam. And we'll accelerate the electrons up to about 20 GeV, 20 billion electron volts. And then they'll go through what's known as a Wiggler system, right? And that will create an X-ray free electron laser. So you'll get a very intense beam of X-rays. The X-rays will be something like 45 keV, 45,000 electron volts. And they'll be able to give us a bunch of X-rays about every billionth of a second. And the X-rays will be of a width of a few picoseconds, okay, a few trillionths of a second. So incredibly high time resolution and able to follow very fast dynamic systems. Okay, and so the main point of Marie is to really understand, so you probably figure out why the laboratory needs to understand how materials behave in very harsh environments, right? And what we'd like to be able to do, right, when we used to do to build a nuclear weapon is you'd had a design and then you would take it to Nevada and you would test it and you would see if it worked. We no longer do that, right? So we have to take a design and run computer codes and determine if things are going to work or not. But we need to be able to do experiments to verify that. And so a lot of those experiments are based on understanding material properties, right? Materials are incredibly complicated things, right? You just imagine, take a potato chip and you say, okay, I'm going to take this potato chip and I'm going to try to break it. Try to predict how it's going to break. right? You take two different potato chips and you do the same thing, you're going to get a different answer. Why did you get a different answer, right? Trying to understand at that level how materials behave is really the main point of Marie. And trying to tie that back into how did we do the manufacturing process, right? So you can change the manufacturing process and that will change the performance of a material. And understanding that link as we have to change components in the stockpile is very important for the laboratory. And so that's really the main purpose of Marie. And we're hoping that sometime in the late 2020s, we'll actually have the facility here. But that will be the most intense X-ray light source in the world at the time.
Will you